A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
Have you ever stopped to really look at a periodic table? Have you really looked at it? Most of us remember it as that colorful, grid-like poster hanging in the back of a high school chemistry classroom. Maybe something we had to memorize for a test and then promptly forgot. But when you dig into what it actually represents, it is probably the most successful piece of information architecture in human history. It is not just a list of ingredients for the universe. It is a map of the fundamental constraints of reality. Our housemate Daniel sent us a prompt today that really gets to the heart of this. He was asking how it is possible that this list seems fixed in time, what the last element discovered was, and whether the list is actually definitive, or if there is a whole frontier of matter we have not touched yet.
Herman Poppleberry here, and Corn. I have been waiting for a prompt like this. It is a fantastic question because it touches on the bridge between chemistry and high-energy physics. Most people think of the periodic table as a finished map, like a map of the continents where we have already found everything there is to find. But in reality, it is more like a map of a coastline where the tide is constantly shifting, and we are trying to see how much further the land goes before it just drops off into an abyss of physical impossibility. We are currently standing at the edge of the known world, looking out at element 119 and 120, wondering if the ground will hold beneath our feet.
I like that analogy, and I think we should start by addressing Daniel's question about what makes an element in the first place. Because if you do not understand that distinction, the rest of the table just looks like a random collection of names. We talk about compounds and molecules all the time, but an element is something much more primal. It is the difference between a specific type of Lego brick and a castle built out of those bricks.
You've got it. The fundamental distinction is the proton. If you have a single atom, the number of protons in its nucleus is its identity. That is the atomic number, which we represent with the letter Z. If you have 6 protons, you are carbon. It does not matter how many neutrons you have. It does not matter how many electrons are buzzing around or what other atoms you are bonded to. 6 protons equals carbon. Period. A compound, on the other hand, is a social arrangement. It is what happens when 2 or more elements decide to share or swap electrons to find a more stable energy state. Water is a compound because it is 2 hydrogen atoms and 1 oxygen atom holding hands via their electrons. But you can break that bond. You can use electricity to split water back into hydrogen and oxygen. You cannot split an element into a different element using chemical means. To change the element itself, you have to go into the nucleus and change the number of protons, and that requires the kind of energy you only find in stars, supernovae, or multi-billion-dollar particle accelerators.
So the periodic table is essentially an organizational chart of proton counts. 1 proton is hydrogen, 2 is helium, and so on, all the way up the line. It feels fixed because the sequence is logical. There are no gaps between 1 and 118. We are not going to suddenly discover an element between carbon and nitrogen because you cannot have 6.5 protons. It is a discrete digital count of the universe's building blocks. But Herman, even with that logical sequence, the table has grown quite a bit in our lifetime.
It really has. If you look at a textbook from 30 or 40 years ago, the bottom row of the periodic table looked like a construction site. There were a lot of placeholders with weird 3-letter names like un-octium or un-septium. But as of right now, in March of 2026, that 7th row is completely filled. The last element to be officially recognized and named was element 118, which is Oganesson. It was named after Yuri Oganesson, a Russian physicist who is basically the grandfather of superheavy element synthesis. And what is wild is that Oganesson was synthesized back in the early 2000s, but it took years of verification and peer review before it was officially added to the club.
I want to talk about that synthesis process because I think it addresses another part of the prompt. Daniel asked if the list is definitive. When we talk about discovering element 118, we're not talking about finding it in a mine in Siberia or in the atmosphere of a distant star. We are talking about creating it. It does not exist naturally on Earth.
That is a crucial point. Everything beyond element 94, which is plutonium, is essentially synthetic. You might find trace amounts of some of them in specific stellar environments or as decay products, but for all practical purposes, if we want to see them, we have to build them. And the way we do that is through high-energy ion accelerators. Imagine you want to make element 118. You cannot just keep adding one proton at a time, the nucleus becomes too unstable too quickly. Instead, you take a heavy target like californium, which has 98 protons, and you blast it with a beam of calcium ions, which have 20 protons. 98 plus 20 equals 118.
It sounds simple when you put it like that, like simple addition, but I imagine the physics of getting those two nuclei to actually fuse is a nightmare. They are both positively charged, so they want to repel each other with incredible force. It is like trying to push two magnets together when the north poles are facing each other. But the magnets are the size of a grain of sand, and you are throwing them at each other from a mile away.
It is the ultimate game of cosmic billiards. You have to accelerate those calcium ions to about 10% of the speed of light. If they are too slow, they just bounce off the target due to the electrostatic repulsion, which we call the Coulomb barrier. If they are too fast, they smash the target nucleus to pieces. You have to hit that Goldilocks zone where they overcome the repulsion and the strong nuclear force takes over, snapping them together into a single, massive nucleus. And even then, the success rate is vanishingly small. You might run an experiment for months, smashing trillions of ions into the target, and end up with only 3 or 4 atoms of the new element. And those atoms might only exist for a millisecond before they decay into something lighter.
This is where I think people get skeptical. They hear that we spent millions of dollars to create 3 atoms that disappeared in the blink of an eye, and they wonder, what is the point? Is this just scientific trophy hunting? Or does Oganesson actually tell us something about the nature of reality?
It is definitely not trophy hunting. It is about testing the limits of the standard model of physics. You see, as we get heavier and heavier, the rules of chemistry start to get weird. We expect elements in the same column of the periodic table to behave similarly. Oganesson is at the bottom of the noble gas column, right under radon and xenon, so theoretically it should be an inert gas. But because its nucleus is so massive and it has so many electrons, we predict that relativistic effects start to kick in. The electrons in the innermost shells are moving so fast, approaching a significant fraction of the speed of light, that they actually gain mass and contract. This changes the way the outer electrons behave. There are theories that Oganesson might not be a gas at all at room temperature, and it might actually be somewhat reactive, which would break the periodicity of the table.
That's a wild thought. So the periodic part of the periodic table, the idea that properties repeat in a predictable pattern, might actually have an expiration date.
That's the core of it, and that leads us to one of the most exciting theoretical concepts in nuclear physics, the island of stability. Most of these super-heavy elements we create are incredibly unstable. They have half-lives measured in microseconds. But physicists have long theorized that if we hit certain magic numbers of protons and neutrons, numbers that create completely filled nuclear shells, similar to how noble gases have filled electron shells, we might find isotopes that are much more stable. We are talking about elements that might last for minutes, days, or even years. If we could reach the island of stability, we would not just be looking at fleeting ghosts in a detector, we might be looking at entirely new materials with properties we cannot even imagine.
You mentioned magic numbers. What are we looking at for this island of stability? Are we close to it?
The consensus is that the center of the island is somewhere around element 114, flerovium, or maybe element 120 or 126. But the real key is the neutron count. We need a specific number of neutrons, likely 184, to reach the peak of that island. We have already synthesized flerovium, but the isotopes we have made so far are neutron poor. They do not have enough neutrons to reach that peak stability. To get there, we need better ways to shove more neutrons into the nucleus during the fusion process. It is like trying to build a stable tower out of blocks, but we are currently missing the specific size of block that holds the whole thing together. If we can find that right combination, we might unlock a whole new chapter of the periodic table that is not just a list of radioactive casualties.
I love that image of the island of stability. It makes the periodic table feel less like a finished document and more like a treasure map, where we know the coordinates of the treasure, but we just have not built a fast enough boat to get there yet. But let us look at the other side of that coin. Is there a hard limit? If we keep going to element 120, 150, 200, does the universe eventually just say no?
There is a theoretical limit, and it is often called the Feynman-Mendelssohn limit. It goes back to what I mentioned about relativistic effects. As the number of protons increases, the pull on the innermost electrons becomes so intense that they have to move faster and faster to avoid falling into the nucleus. At a certain point, around element 137, which some people call Feynmanium, the required speed for an electron in the lowest energy state actually exceeds the speed of light. Since nothing can go faster than light, the traditional model of the atom essentially breaks down. Now, more modern calculations that account for the fact that the nucleus is not a single point but has a physical volume suggest the limit might be higher, maybe element 172 or 173. But regardless of the exact number, there is a point where the electromagnetic repulsion between all those protons simply overcomes any possible amount of strong nuclear force you can provide with neutrons. The nucleus becomes so large that it cannot even hold itself together for the time it takes for an electron shell to form. At that point, you do not really have an atom anymore, you just have a momentary blob of nuclear matter.
That really puts the fixed-in-time question into perspective. The table is fixed because it is governed by the fundamental constants of the universe, the strength of the electromagnetic force versus the strong nuclear force and the speed of light. It is not a human invention. It is a human discovery of a cosmic boundary. It reminds me of what we discussed back in episode 734 about the chaos of timekeeping. We try to impose these very rigid structures like UTC and atomic clocks on a universe that is fundamentally wobbling and expanding. The periodic table is our attempt to categorize the stuff of the universe, but the further we push to the edges, the more the universe resists our neat little boxes.
It really does. And those relativistic effects are not just limited to the super heavy elements we make in labs. They actually affect elements we use every day, which I think is a great bridge to the practical side of Daniel's prompt. Take gold, for example. If you look at the periodic table, gold is right below silver and copper. Based on its position, gold should look like silver. It should be a bright, colorless metal, but it is yellow. That color is actually a relativistic effect. The electrons in gold are moving so fast, about half the speed of light, that their energy levels shift. Specifically, the 5d and 6s orbitals move closer together in energy. This causes the gold atoms to absorb blue light and reflect yellow and red light. If it were not for Einstein's theory of relativity affecting the atoms, gold would look just like silver.
Wait, really? So the very thing that makes gold, the thing that has driven human economy and jewelry for thousands of years, is a result of the electrons moving at near light speeds?
Precisely. And it is the same reason mercury is a liquid at room temperature. The relativistic contraction of its electron shells makes the atoms much less interested in bonding with each other. They stay separate and fluid rather than forming a solid lattice. When we talk about the periodic table, we are talking about the deep architecture of reality. It is not just a list of names, it is a description of how energy and mass are allowed to exist together. It is why we can predict that element 119, which is currently being hunted by teams at RIKEN in Japan, will likely be an alkali metal, similar to lithium or sodium, but with even more extreme properties.
This brings up a point about the one-size-fits-none concept we touched on in episode 690 regarding precision medicine. We often want nature to be simple and uniform. We want every carbon atom to be identical, and every gold atom to be identical. And they are, in terms of proton count. But once you start looking at isotopes, atoms of the same element with different numbers of neutrons or isomers, where the nucleus is in a different energy state, you realize that even within a single entry on the periodic table, there is a massive amount of diversity.
That's a sharp connection, Korn. People often confuse elements with molecules, but the element is just the species of atom. Carbon is the species. But carbon can be a diamond, it can be graphite in your pencil, or it can be a carbon nanotube. Those are all made of the exact same element, but the way the atoms are arranged. The social arrangement I mentioned earlier changes everything. Daniel's prompt asked what distinguishes an element from a compound. In practical terms, it is about the level of reduction. If you have a piece of pure gold, every single atom in that piece has 79 protons. If you have a molecule of carbon dioxide, you have a carbon atom and 2 oxygen atoms. You can chemically separate them. You cannot chemically separate the protons from a gold atom without turning it into something else entirely, which is the realm of nuclear physics, not chemistry.
So, when we look at the future of the periodic table, we are really looking at the frontier of high-energy physics. We are currently at element 118. Scientists are already trying to synthesize elements 119 and 120. There is a huge effort at the RIKEN facility in Japan and at the Joint Institute for Nuclear Research in Russia to find that next row. They are using beams of vanadium and titanium now, trying to find the right combination to stick to targets of curium or berkelium. But as we have discussed, it is getting harder and harder. Each new element requires more energy, more precision, and more time.
It really is a feat of engineering as much as physics. You need detectors that can identify a single atom decaying in a sea of background radiation. You need targets that can withstand being bombarded by high-energy ion beams without melting. It is incredibly difficult work, but the payoff is a deeper understanding of the strong force that holds the entire universe together. If we can understand why element 120 is stable or unstable, we understand more about why stars shine and how the heavy elements in our own bodies were forged in the first place. Most of the elements in your body were made in the hearts of dying stars, but these super heavy elements are being made in the hearts of human-made machines.
I think that is a key takeaway for the listeners. The periodic table is not just a static chart, it is a living record of our attempt to map the limits of matter. When Daniel asks if it is definitive, the answer is yes and no. It is definitive in its logic. We know exactly where the next elements will go if they exist. There is no room for a surprise element between hydrogen and helium, but it is not definitive in its completion. We are still adding to it. We are still finding those islands in the sea of instability. And every time we add a new square to that grid, we are essentially confirming that our understanding of the universe's laws is correct, or even more excitingly, we are finding out where those laws start to break.
I love that. We should also mention that the periodic table is a predictive tool. Mendeleev, the guy who originally formulated the modern version, left gaps in his table because he knew, based on the patterns, that certain elements had to exist even though they had not been discovered yet. He even predicted their properties, their density, their melting point with incredible accuracy. Today, we are doing the same thing with the super heavy elements. We are predicting what element 120 will look like before we have even seen a single atom of it. We expect it to be an alkaline earth metal sitting right below radium. That kind of predictive power is rare in science. It shows that the universe has a deep underlying grammar.
It really is. It is the ultimate proof that the universe is not just a random collection of stuff. It is a structured system. And as we move forward, especially as we look at the possibility of reaching that island of stability, we might be entering an era where we can design materials at the nuclear level, not just the molecular level. Imagine if we found a super heavy element that was stable and had superconducting properties at room temperature, or something even more exotic. We are currently limited by the materials nature gave us, but the island of stability suggests there might be a whole different set of materials waiting for us if we can just figure out how to reach them.
That is the dream. It might be a long shot, but the history of science is full of people saying something is impossible right before someone else does it. We have gone from thinking the atom was an indivisible plum pudding to smashing nuclei together at 10% the speed of light. I would not bet against us finding a way to the island of stability. Even if we only find isotopes that last for a few days, that is enough time to start doing real chemistry with them, to see how they bond, how they behave, and how they challenge our understanding of the electron shells.
Well, Herman, I think we have given Daniel a lot to chew on here. To recap for everyone listening, the periodic table is fixed in its sequence because it is based on a simple count of protons, but it is an expanding frontier in terms of what we can actually synthesize. Element 118, Oganesson, is our current boundary, but the search for 119 and beyond is very much alive. The difference between an element and a compound is the difference between an individual's identity and their relationships. And finally, the table is governed by the laws of relativity and nuclear physics that define the very limits of what can exist in our universe.
Beautifully summarized. It is easy to take that little poster in the chemistry lab for granted, but it really is the autobiography of the universe. Every atom in your body, every breath of air, which we talked about in episode 565, the invisible soup episode, it is all accounted for in those 118 squares. And as we push toward element 120 and 126, we are essentially asking the universe how much more it has to give.
One last thing, Herman. Do you think we will ever see element 137 in our lifetime?
If we do, we are going to need a much bigger accelerator and maybe a new theory of how electrons work. But hey, never say never. We might just find a way to sail past the Feynman limit.
I hope so. I think Daniel is making dinner tonight, and I am starving. I just hope it is not another experimental compound. Last time he tried to make that molecular gastronomy foam. It tasted like element 118, and slightly metallic.
As long as it is made of elements we recognize, we should be fine. No super heavy isotopes in the pasta, please.
Agreed. I couldn't agree more. And if you're listening and you want to dive deeper into how these fundamental constants shape our world, definitely check out our archive at myweirdprompts.com. We have got over 1,000 episodes now, covering everything from the physics of time to the future of medicine. You can search the whole collection there, and if you have a weird prompt of your own, there is a contact form right on the site. We love getting questions like Daniel's because they force us to look at the mundane things, like a classroom poster, and see the cosmic drama hidden inside them.
And hey, if you've been enjoying these deep dives, do us a huge favor and leave a review on Spotify or wherever you get your podcasts. It really helps the show reach more curious minds like yours. We genuinely appreciate the support from our community. Every review is like adding a neutron to our stability. It keeps us going a little longer.
My Weird Prompts is a production of the Poppleberry Brothers. You can find us at myweirdprompts.com. Thanks for joining us for another episode. I am Corn Poppleberry.
And I am Herman Poppleberry. Thanks to Daniel for the prompt, and thank you all for listening. We will catch you in the next one.
Stay curious, everyone. Goodbye.
Goodbye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow